All right, so hello and welcome back to another session of OneClass. Again, my name is Joey. I'm going to be your chemistry teacher for today. So for the next for the next hour, the hour after, what we're going to do is we're going to answer and verify some of these solutions sent in by you folks at home, in terms of in the topic of secondary school level chemistry. So in this first hour, what we're going to do is that we're going to answer questions kind of asked in about grade 9 to grade 11 chemistry courses, questions pertaining to those subjects. And then the next hour, the next stream, what we're going to do is we're going to answer some of your questions in terms of grade 12 chemistry, so kind of the senior level chemistry course there. So again, my name is Joey. I come from a background of having a bachelor's of science in chemistry. I'm a secondary school educator. So my specialized subjects are chemistry and math. So with that knowledge, I'm hoping to help you teach concepts through these questions so that you're better prepared for tests and for other future courses. If you're tuning in for the first time, again, thank you for watching. Here at OneClass, just a little bit about ourselves is that OneClass kind of aims to create these online live streams and videos, and we upload them onto YouTube for all students to kind of follow, so that you'll be able to kind of grab the correct solutions for your courses, so that you're better prepared for your assignments or tests and upcoming assessments. So we make online learning accessible, and what we're doing now is, because of the school closures, we're providing an opportunity for you to learn at home in the comfort of your own home, without missing much from school. So with that being said, let's get started on today's questions. All right, so let's look at the first one here. It's looking at how do valence electrons determine chemical reactivity. So, kind of a basic question here to start off our day with. But let me write this down first. So it's asking, this is number 1. It's asking how do valence electrons determine chemical reactivity. So take a moment to think about this question. It's asking, first, we have to understand this topic of what are valence electrons and what's chemical reactivity have to do. So take a moment to think about this question. Maybe if you're in the chat, again, feel free to answer this question for me as well as we're going through these questions. So these are the two kind of key points here. What are valence electrons? And how do we determine chemical reactivity? So take a moment to think about that. So when we're talking about chemical reactivity, we're talking about how substances undergo chemical changes, chemical properties such as like combustibility or flammability or chemical change are all kind of components to chemical reactivity. It's how it reacts with other substances. So let's define these terms here. I'll do some blue. So we're undergoing, this is chemical change with other substances. So you can think of it as it's either being broken down, being used as a reactant to create a new product, being displaced or being oxidized or being burnt. All these are chemical reactions. So chemical change with other substances, so that's reactivity. And then obviously for valence electrons, remember we know that valence electrons are they're in the highest energy level of the atom. So they're the electrons in the outer shell. So if you think back to your Bohr-Rutherford diagram that we've been doing throughout grade 9 and 10, we can draw a Bohr-Rutherford diagram, and we know that the outside electrons here, the electrons exist on the outer shell, are called the valence electrons. So with that being said, how do valence electrons determine chemical reactivity? So for example, if I had something like lithium, and if I draw the Bohr-Rutherford for that one, so I have lithium here, and I'm gonna I have two energy levels, right? I have the first shell has two valence electrons, and then the last one has 1, right? Has 1 here. So I have lithium has again 1 valence electron at its outer shell. Lithium is actually really reactive. Lithium is reactive to water, and why is that? Why is it reactive? Because it's so close to getting a full shell, the shell of 2, if this electron leaves. And this here is the valence electron, right? Sorry, valence. I'll do valence. E minus here for electron. In this, if this valence electron goes away, if it's being bonded to, let's say, hydrogen or something like lithium hydride, it becomes very, very reactive. It's very, very reactive in water as well. Again, this hydrogen is going to cling onto this this lone electron here. Those are very, very, very attractive forces. So in this case, it's a very reactive substance. Lithium is reactive here because it only has 1 valence electron. And same with if I had the opposite one. If I have, for example, fluorine I have, so let's see, I have 2 electrons in the first shell. And then I'm going to have 7, right? 1, 2, 3, 4, 5, 6, 7. I have 7 valence electrons in the second shell here. And this is also very reactive, right? And why is it reactive? Because it only needs 1 more electron, right? If an electron is being donated here, it makes a full shell. So fluorine here reacts very, very heavily with hydrogen, for example, or with acids. A proton donor would be very, very reactive with fluorine here. So again, all these ones are like these guys here are valence electrons determine chemical reactive. If they're close to achieving a full shell, they are very, very much reactive here. So let's look at the solution here. So step 1, the valence electrons participate in the formation of chemical bonds. This here is correct, right? Because the valence electrons basically dictate the energy level of the element firstly, and it also dictates on how those electrons are being moved to create new chemical compounds. So that's the property of reactivity here. Elements in which the valence electrons are either fulfilled or half-filled are extra stable and therefore less reactive, right? So again, if they didn't have this, if it was only like maybe 4, like carbon or something like that, it's not as reactive than lithium and fluorine here. And it says here, the elements in which the valence electrons are partially filled are not stable and have a tendency to complete their octet either by loss of gain of electrons, right? So in this case, for lithium, we have a loss of electrons, right? We want to lose this last electron for us to get a full shell of 2, and this one we want to gain our electron, right? We want to gain 1 to get a full shell of 8, right? So this here is the correct answer, therefore they're highly reactive. So I said lithium and fluorine are highly reactive, and for example, carbon is not as reactive because it has, again, carbon here, if you look at the periodic table, has only 4 valence electrons, so it's kind of exactly in the middle, so they're half filled. So carbon by itself is somewhat stable. Okay, so I'm going to say this solution is correct. It's correct. Good analysis. Solution is correct. Sweet. That's number 1. Let's look at number 2. Number 2, we have a list of solids here. It says classify each of these solids as ionic, molecular, or metallic, or covalent. So we have C, which is a diamond. So I'm going to say this is a diamond. We have CCl4. We have Ca, and we have CaCl2. And we are supposed to know whether they're ionic compounds, molecular compounds, metallic, or covalent. So let's look at this question here. So again, what we have to do is, so they answered this problem already. It says metallic, molecular, ionic in the given order, but I don't think they answered this one as well. Oh, they only answered 3 of the problems and not, we have 4 chemicals here, right? They only answered 3. So again, I guess my solution here is incorrect in this case. I have 4 compounds here. So let's look at number 1 here. Number 1 here, we get a carbon, which is in the shape of a diamond, right? So in the shape of a diamond, we have basically carbon-carbon bonds attached to each other. If you look at the chemical kind of compound of diamond, it's very, very similar to how the network of carbons is kind of bonded like graphite. Graphite is another kind of carbon-based compound that has many carbon to bond to carbon bonds. So as you can probably tell, carbon can make 4 bonds, and we know that it's going to bond to another carbon who's going to make 4 bonds, and etc. Right? So this here is going to bond to each other, and like so on and so forth. Right? So again, this here makes a very, very rigid structure, right? Because again, these guys are very, very stable. And basically, if we have a network of carbon-carbon bonds, we are what would that be? Would that be ionic? It would not be. It would be a molecular. It would not be as well. So in this case, it would be a covalent bond, right? So a covalent bond, we have 2 nonmetals. Carbon is a nonmetal here, and this compound could be treated as a covalent bond, right? So the first one here would be in terms of it has a covalent network. So you can say that this here is a covalent compound. Let me do this in blue. This is a covalent compound, or you can say covalent network, etc. as well. Graphite, again, is one of those compounds. Diamonds is also one of those compounds, and whatnot. So that's covalent here. Let's look at number 2. Number 2, we have CCl4. So CCl4, and what compound would this be? Or how would I label this compound? Again, all we have to do is look at the chemical formula, right? Our first guy here is carbon, and we know carbon here is a nonmetal. You can look at the periodic table if you need help with this. So let me look at the periodic table. And as you can see, carbon exists on this right side here. It's under nonmetal, so you know it's a nonmetal here. Cl4 is chlorine, and chlorine is also a nonmetal, right over here. Chlorine is number 17, and this is a nonmetal as well. So Cl would mean that this here is also a nonmetal. Here is chlorine, and this here is a nonmetal as well. Which means if you have we have nonmetals bonded to a nonmetal, this is a good example of a molecular compound. And what we can do is we can actually name this as well. We know this is simply just carbon tetrachloride, right? Carbon tetrachloride, because we have four chlorines here. So 4 chlorines means it's the prefix of tetra, so it's carbon tetrachloride. Here would be our chemical name for this compound. Here we follow the molecular naming here. And we have Ca and CaCl2. So let me write this down here. So we have we have CaCl2. So let's look at Ca here. We have this metal here. This is calcium, right? Ca here is calcium, but it's not bonded to anything. So in this case, calcium, if it's not bonded to anything, you don't really have you have a solid. This is simply just a metal, right? But it's not, you can't classify calcium in terms of these compounds here. We have ionic, which is a metal and a non-metal. Molecular is a non-metal and non-metal. Metallic is a kind of special solid where it has kind of a multivalent compound here. And in this case, calcium has a charge of 2+, right? Calcium has a charge of 2+, which means it's not multivalent. So in this case, we don't have a metallic bond going on. And then covalent is simply just a network of carbons, right? So or a network of carbons basically. So in this case, it's actually none of the above. Carbon, calcium here 2+ belongs to none of these options here. It's simply just a metal, right? And we can't really label this metal as anything else because it's a solid, but it's not a molecule. You don't have like 2 elements put together. But however, if you look at calcium chloride here, calcium chloride is different, right? You have calcium here, Ca is calcium, and chloride is chlorine, right? So we have 2 elements here. We have calcium here is a metal here, and chlorine is a non-metal. So if you have a non-metal and a metal here, you can simply infer that if you have one thing on the left side of calcium, and then you have chlorine on this side, again, you can make the assumption that this here is an ionic compound. So this here would be our answer here. We have kind of covalent, molecular, metal. So again, it doesn't belong to any of these categories here, and the ionic would be our answer. So I'm going to say this solution is incorrect because they only gave me 3 answers. So this solution is incorrect. And then I'm going to have to say carbon diamond is covalent, is formed through a covalent network of carbon atoms. This is CCl4 is a molecular compound, non-metal bonded to a non-metal. Ca here is simply just a metal, does not belong to any of these categories. And CaCl2 is an ionic compound, metal and a non-metal. Sweet. Solution here is incorrect, I'm going to say, because it only gave me 3 answers here. Sweet. That was number 2. So now we can move on to number 3 here. So it says identify the elements that have molecules as their basic unit. So I have identified the elements that have molecules. So molecules as their basic unit. So I have A here, which is hydrogen. B here is iodine. C here is lead. And D here is oxygen. So it says identify the elements that have molecules as their basic unit. So when we talk about molecules, we're talking about basically elements that have it's basically 2 or more elements, right? So let's define this term molecule. So again, molecule are basically 2 or more elements, and they're also bonded to each other, right? Bonded to each other. So knowing that molecules are 2 or more elements are bonded to each other, we can then look at the chemical formula of these guys here to figure out if it's a molecule or not, right? Hydrogen, again, hydrogen, we know it's a special kind of element here. Hydrogen gas kind of exists as 2 parts, right? So we know hydrogen is H2, right? H2. And in this case, this would be a molecule, right? Because I have more than one. So which means this here is a molecule. And again, this is a great example of diatomic molecules, right? So when we talk about this concept of, and I'm going to do a subsection here. This is the topic of diatomic molecules. And then I have like a kind of a mnemonic to help us memorize this. So it's Hofbrinkel, right? So it's H-O-F Brink I-N-C-L. Hofbrinkel. So it's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. All these guys here exist always in 2. So they always exist in 2 or in pairs. So iodine here belongs in terms of my diatomic, which means the chemical formula for iodine is I2. So therefore this here is also a molecule. Lead here is simply, if you look at the chemical formula for lead is actually over here, right? It's Pb here. This is number 82, Pb. And this here is not a diatomic molecule, right? Which means I can simply put Pb by itself here. And if I only have one of the element here, this is not a molecule here, not a molecule. And the oxygen is again in my diatomic, right? Hof, the O here means oxygen. So this here is O2. So it exists in 2, therefore this here is a molecule. So in this case, A here is a molecule, B here is a molecule, C is not a molecule, and D here is a molecule. So this here is my correct answer. A, B, and D are all molecules. So let's look at the answer here. It says the elements have molecules as their basic units. A, hydrogen has molecules, that's good. Iodine has molecules, that's good. Lead does not, and oxygen has molecules, that's good. So it says molecular element do not has do not has, this grammar is not very good, don't have a single atom as a basic unit and exist as molecules in which two or more atoms of an element are bonded together. The molecular elements are usually diatomic. That's what I said here. That's good. The chemical formula of hydrogen is, they repeated the exact same statement here, and then they repeated the exact statement here. So this solution is correct. I just don't like their formatting. The solution is correct. I'm not a fan of the formatting of the answer, but remember, diatomic molecules are diatomic molecules consist of, and then I can say hydrogen. I can list hydrogen, oxygen. This is fluorine, bromine, iodine, nitrogen, and chlorine. Lead is not a diatomic molecule. Yeah. While the rest are. So the solution here is correct. Awesome. Let's look at question 4. It says, which statements about subatomic particles are false? Let me just write down these 4 statements here. So A here is I'm looking for the false answer here. So it says protons and electrons have charges of the same magnitude but opposite signs. B here says that protons have about the same mass as neutrons. So I'll just simplify this. Mass of protons equals mass of neutrons, are approximately here. C states that some atoms don't have protons. And D here's protons and neutrons have charges of the same magnitude but opposite signs. Neutrons have charges of the same magnitude but opposite signs. Okay, so we have all these statements here. So let's look at the first statement here, and we're trying to figure out the false one here. So protons and electrons have charges of the same magnitude but opposite signs, right? So this solution here is correct, and so we know that this is a true statement, so it's not the false statement. So this here, I can say this is wrong because protons and electrons have opposite signs, right? So we know protons are positive, that's good. Electrons here are negative, so protons are positive, electrons are negative. So they have the charges of the same magnitude. That's great because one negative charge balances out another positive charge, but they have the opposite signs. So this solution, this answer here is true. This statement is true, and we're trying to figure out the false statement, right? So I immediately cancel this. Mass of protons, so let's look at B. Mass of protons is about the same mass as mass of neutrons. This here is also correct, right? When we're talking about atomic mass, we count protons as one atomic mass unit and neutrons as one atomic mass unit, right? So this here is also true, which means this cannot be our answer here. Remember, the mass of protons is 1 AMU, and then 1 AMU for our mass of neutrons. The only one that's not 1 AMU is electrons. Right? The mass of electrons are extremely, extremely small. C, some atoms don't have any protons. So this here is also this. So this statement is kind of odd when they say some atoms don't have protons. So this solution is actually is true. And when we say some atoms don't have protons, it means when we're talking about atoms, we're talking about atoms are kind of made up of, like some atoms could just have electrons, or just have protons and whatever, right, and whatnot. So you could have an atom that theoretically does not have a proton, but this here is an iffy answer. So I'm gonna leave that. Because I don't really like the wording here. Some atoms don't have any protons. I don't really like the wording on this one. So I'm going to skip to the D here. D here, protons and neutrons have charges of the same magnitude but opposite signs. Protons have a charge of a positive one. Neutrons here have a neutral charge. They have no charge here. So they have charges of the same magnitude but opposite signs. So in this case, they don't have opposite signs, right? One's a positive and one's a no charge. So this solution here is false, which means this solution will be D here is our correct answer for this problem here. So what they wrote here is, again, a very long text here. Some atoms don't have protons. Again, I don't think this answer here is correct either. Just because it says some atoms don't have protons, again, all atoms are made up of three things, right? They're made up of, or the simplest one, hydrogen. Even hydrogen is our simplest atom here. Or let me write this down. Hydrogen is made up of one proton plus one electron, right? So if the simplest atom has a proton, some atoms don't have protons. This here is also false, right? So I can say that C and D here are the false statements because again, I can take hydrogen as the first example, and all atoms contain protons here. So let's check. The statement protons and electrons have charges is true about subatomic particles. So this here is true. That's good. That's what we said here. So it's the wrong answer. The statement about protons is also true. That's good. So that's what we have here as well. The statement some atoms don't have protons is false about subatomic particles. And indeed, the statement protons and neutrons have charges of the same magnitude but opposite signs is also false, right? So this here is also false. So we matched the same answer here. Good. A here just kind of backs up the theory behind this. How do we don't know protons are positive and electrons are negative? Because Rutherford kind of discovered that through his famous experiment. B here, we had Chadwick, who discovered a neutral presence in the nucleus that has the same mass of a proton. That's good. C here's every atom has a proton in its nucleus, right? So again, even the simplest atom here, the hydrogen atom, has a proton, right? That's good. And then D here, proton does not have any charge of it. This is neutrons here. Neutrons so this statement here is neutrons does not have any charge on it because it's neutral, not protons here. So I'm gonna correct their solution. So great solution, but I think you meant neutrons in the statement, and I'm going to copy and paste here. So I'm going to say solution here is correct. Great solution and answer. So this is number 4. Let's look at number 5. We're on track to finish 10 questions today, which is awesome. So it says name the compound HNO3. So this is name the compound HNO3. This is an aqueous solution, right? And this here, I have A here, which is hydrogen, nitrogen dioxide. C here is hydrogen nitrate. This is B, sorry. C here is nitric acid. D here is nitrous acid. So take a moment to think about this question. It says what is the compound HNO3, right? So HNO3 consists of so we have to first break it down into what we want to break this down into our two kind of elements here. So let's break this down first, and we'll look at our naming for this guy here. So when we look at our chemical formula, we have H, and then we have NO3, and we have AQ, right? So this is a big giveaway that this here is an acid, right? So this compound here is an acid. And why do we know it's an acid? The big giveaway is this aqueous solution here. And another big giveaway is there's a hydrogen in front of the compound here. So these two, more so like 99% of the time, states that this here is an acid. And this here would be this here would be an oxy acid specifically. So this here is an example of an oxy acid. So how do we name an oxy acid knowing that? Well, knowing if it's oxy acid, A and B are definitely the wrong answers, right? Because I have an acid here. So it's either C or D as our answer here. So let me write this down in blue, and I'll write down the oxy acid naming rules here. So we have HNO3. What we can do with HNO3 is break this down into its elements here, right? So we have H plus here, which is hydrogen here, and we have a polyatomic ion, which is NO3 minus, right? So this here is hydrogen. If we were to name this by itself, this is hydrogen, NO3 is nitrate, right? So this here was B here, but we know this is an acid, so this here is not its name. So this here is hydrogen and nitrate. And what we can do with this one is we want to follow how to name our oxy acids, right? So in order to name our oxy acids, what we do is we eliminate the hydrogen, right? We drop the hydrogen in its name. We drop the hydrogen in its name, and we add acid to the name after, right? So this here is nitrate acid. And then what we can do is we can drop the ATE here. We change the ATE here into IC or IC. So we change ATE into IC. So this compound here is nitric acid. So C here is our correct answer. So this here HNO3 is nitric acid. Now you might say, okay, what's nitrous acid then? Well, nitrous acid would be not HNO3, this would be HNO2, right? So if I had HNO2, for example, if I had HNO2, I would have nitrous acid, and I'll show you why I have nitrous acid. So HNO2, again, is made up of H, which is the hydrogen, and it's not NO3 here, it's NO2, right? So it's not nitrate, but it's nitrite. So this is nitrite with the ITE. So in oxy acids, what we do is if we have an acid like this, what we're going to do with this, we drop the hydrogen, we add an acid. But if we have an ITAE ending, we are going to change ITE here to S. So OUS here. OUS here. OUS. So this is nitrous acid. So nitrous acid is HNO2, nitric acid is HNO3. So again, if I want to do ATE would become IC acid, and the ITE would become US acid. That's kind of the rules for our oxy acids when we're naming oxy acids here. So this here, C is the correct answer. It's nitric acid. So answer, the name of the compound is option D, nitrous acid. So again, this solution here is wrong. The given compound contains a hydrogen and an oxy anion containing a non-metal nitrogen and an oxygen, which is nitrate. That's good. The given compound has an oxy and a nitrite. So they thought that HNO3 here is nitrite, when in reality it's nitrate. Therefore, they wrote that this is nitrous acid. So this solution is incorrect. The correct name for HNO3AQ is nitric acid because it contains hydrogen and nitrate. Following oxy acid rules. Oxy acid naming rules. This compound would be named nitric acid. 8 becomes IC and add the acid. Or drop the hydrogen. 8 becomes IC and add the acid. So solution here is incorrect. Okay, Sweet, that was number 5. Let's look at number 6. How many valence electrons does bromine have? So this is a very, very easy question here. So valence electrons of bromine. So I'm assuming that this would be asked in kind of a grade 9 setting, right? So again, how many valence electrons are of bromine? So what we can do is we can draw a Bohr-Rutherford diagram, right? And so we have to do BR here. We put bromine in the middle. And I would have to look at how many shells do I need for bromine, right? So bromine here is not a metal. It's not a metal. It's a non-metal. So it exists on this side. And as you can see, number 35 here is Br, our bromine, right? So we're going to have, let's see, 1 energy level here, 1 shell, 2 shells, 3 shells, and then 4 shells here, right? So I'm going to have to draw 4 shells. So this is my first shell, second shell, third shell, and then our 4th shell, like so. So this here is our very, very big, Bohr-Rutherford diagram. So again, our first shell contains 2 valence electrons. Next shell has 1, 2, 3, 4, 5, 6, 7, 8. Whoops. 8. Next shell has, again, a full shell, 1, 2, 3, 4, 5, 6, 7, and 8. And then finally, our last shell has, let's see, if we're in group 17, our last shell will have 7 valence electrons here, right? So again, 1, 2, and then 3, 4, 5, 6, 7 here. So this here will have 7, 1, 2, 2, 3, 4, 5, 6, and 7. And again, it's asking us the question was, what is the valence electrons of bromine? You can simply just count the electrons. So say count electrons in outer shell. Outer shell. Therefore, there are 7 valence electrons in bromine. So again, this is using the grade 9 approach. We use a Bohr-Rutherford diagram. If you were to be specific, if we were talking in the grade 12 context, what we could do is we could write the electron configuration for bromine, and we could figure out that this also has 7 valence electrons. But I'm assuming that this is asked in a kind of a grade 9 context here. So again, if I want to, I can highlight this in red. I have 1, 2, 3, 4, 5, 6, and 7, right? So I have therefore 7 valence electrons here. So let's look at the answer for this question here. Again, they used the grade 12 kind of approach to use electron configuration to kind of figure out how many valence electrons have bromine, which is totally fine. I just don't know what the context of the question is because it simply just asks me how many valence electrons does bromine have. That's okay. And what they're doing is, this topic number here is 35, so they wrote down the electron configuration of bromine. That's good. So I'm going to verify this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5, right? So remember, this is the 4p2 here, 4s2, sorry. This is 3d10, and then 4p5 would be 1, 2, 3, 4, and 5. That's correct. 1, 2, 3, 4, 5. Yeah, bromine is the 5th one here. And all we have to do is, since the highest energy level is 4, what we can do is we take this, the 4s2 and the 4p5, we're adding 2 and 5 here, which makes 7 valence electrons. So this here is the correct solution. So 7 valence electrons, correct. So this here they justified using the electron configuration, but here we can also justify with the Bohr-Rutherford diagram in this case. Again, the incorrect model, but for the sake of being, if it's asking from a grade 9 perspective, this would be a valid answer. So great solution. Good analysis. So depending on the context of the question and the course related to it, can also draw a Bohr-Rutherford diagram to figure out how many electrons in the outer shell. So that was number 6. That's good. Let's look at number 7 here. So this is a titration type of question. So kind of what you would see in grade 11 here. grade 11, grade 12. So we have 100 ml of 0.200 molars of HCl is titrated against 0.250 molars of NaOH. It's asking what is the pH of the solution after 50 milliliters of acid is added, right? So again, I'm asking, this is saying 50 milliliters for A of acid, and then express the pH numerically, and then it's asking what is the pH of the solution at the equivalence point. Okay, sweet. So let's look at this question here. So it's asking what is the pH of the solution after 50 milliliters of base has been added, right? So how do we figure out pH? Well, we figure out pH by using this formula here. We have pH equals the negative log of our hydronium ion, right? H3O plus, or you can say H plus, depending on what course you're in. I will say H3O plus for the sake of time. And again, it's saying what is the pH of the solution after 50 milliliters of base has been added. So let's look at our acids and base to see if we have a strong base or a strong acid. In this case, HCl here is strong acid. We know that this dissociates fully in water, and NaOH is also a strong base. So therefore, we have a strong acid, strong base titration, right? So therefore, what we can say is that we can say if we have 50 milliliters of 0.250 NaOH, and we have 100 milliliters of 0.20 of 200 milliliters of 0.20 20 molars of HCl, what we can do is we can actually find the moles first of these two compounds to figure out how many moles of each have been used up. So let me erase this first, so we'll calculate pH later. But we're gonna figure out the moles of our solution first. So if we know that we have our volume and we have our concentration, we want to find moles, we have to figure out simply just C equals N over V, right? Concentration equals moles over volume. Therefore, my moles equals concentration over our concentration times our volume here, right? C times V. So let's do our moles of our HCl first. Moles of HCl would equal the concentration of HCl, which is 0.2 molars, times 100 milliliters. But I would have to convert that to liters, right? The SI unit for V here is L. So in this case, this would be 0.1 liters. And then the moles of HCl would simply just equal, this is 0.2 times 0.1, 0.2 times 0.1, which would give me 0.02. 0.02 must be moles of HCl. That's good. And then let's do the moles of NaOH, right? So we have N of NaOH also equals, this is C times V. So this would equal the moles of NaOH of sodium hydroxide is the concentration of sodium hydroxide, which is 0.250 moles times our volume, right? Our volume is 50 milliliters. So we're going to divide that value by 1,000 to get it in liters. So we have 0.05 liters. And then the moles of NaOH we would get is 0.250 times 0.05. This here would be 0.0125 moles of NaOH here. So given that we have 0.0125 NaOH and we have 0.20 moles, what we have is we have actually less than more moles of acid than more moles of base, right? So what we can do is we can actually draw our chemical formula here. So what's actually happening? Oh, sorry, I didn't want to clear all here. So we have HCl is titrated with NaOH, right? So we have HCl here plus NaOH, and then it's going to give us, this is a acid-base neutralization reaction. It will give us NaCl, which is kind of our salt, plus our plus H2O, right, which is our water here. So if we know our moles of HCl is, moles here is 0.02, and moles of NaOH is 0.0125. What we can do is this here will be this is kind of a limiting reagent stoichiometry question, right? The moles of our NaOH is going to be used up first, right? So this here is going to be used up first, and HCl here is our excess reagent, right? So NaOH is going to be used up first. So I can kind of cross this out here, and I can say that we have how many moles of HCl left. We have 0.02 minus whatever 0.125 is left, right? So 0.2 minus 0.0125. This would be, I would be left with here. This is 7.5 times 10 to the negative 3 moles of acid, right? This is moles of acid here. So if we have this left in terms of our HCl, because our NaOH is used up, then we have to figure out our concentration again, our new concentration with this, right? So we have N of HCl, which is simply, this is concentration equals N over V, right? And concentration here is our new moles, right? So we have 7.5 times 10 to the negative 3. This is our moles of HCl after the reaction. And then we have also our volume, which is now the total volume. So we have 100 plus 150, right? This will be our total volume. So 100 plus 50. So we have 150 milliliters divided by 1,000, right? Divide that answer by 1,000, we get 0.15 liters. So this is moles, 0.15 liters is our total volume. And then we simply have to divide 7.5 times 10 to the negative 3 divided by 0.15, and we would get 0.05 as our concentration here, as our concentration of HCl. So this is 7.5 times 10 to the negative 3 of, so this is, let me just double check this, negative 3 divided by 0.15. Yes, this is 0.05 molars. So we have, this is of HCl, right? Of HCl. And because we know it is a strong acid, so we know that HCl dissociates fully. So HCl dissolves fully plus H2O. It's going to dissolve fully into H3O plus and HCl and Cl minus, because we know it's a strong acid. Therefore, my concentration of 0.05 molars is also the same exact concentration of our acid here, which is also 0.05, right? So now what we can do is we can finally use our formula here. pH equals negative log of H3O plus. And then what we have is negative log of 0.05, which is our concentration of our hydronium. So this here would equal negative log of 0.05. This would equal 1.30 would be our answer for this problem here. 1.30 is our pH. So this solution here is number A. So let me just check this for A. This here is correct. They have pH as negative log of 0.05, which is 1.30. Perfect. Let's see what they did here. Moles, they calculated moles good first, and then moles of excess. So this is a limiting reagent question. They did the exact same thing. So 0.02 subtracted 0.0125 here. So I would get 0.00750, which is 7.5 times 10 to the negative 3. They have a total volume of 0.150, which is great. So they found the concentration, which is 0.05. Moles of HCl. They didn't do this step, but they implied that it's a strong acid. So the concentration of my HCl is the same as of a concentration of H3O plus, and this here is 1.30, which is great. And then finally for B, this was part A, right? Part A was our 50 milliliters, and part B is as what is the pH of the solution at equivalence point. So when we talk about equivalence point, we are talking about, so what is equivalence point? Equivalence point means moles of acid equals my moles of base, right? So my moles of acid equals my moles of base. And what we have is we can actually already calculate this. If my moles of acid is 0.02, NaOH would be 0.02. What it's going to do, it's going to cancel out both of these. It's going to use up both of them equally, right? And when we use both of them up equally, we don't have either acid or base, right, in our reaction. So which means this here, we have acid, we have base. It's both strong and both strong acids and strong bases. Therefore, what it's going to equal out to pH 7. So this here is pH 7 because it's a neutral solution. we have the exact same moles of acid and exact same moles of base. So therefore, our equivalence point, which means our concentration of acid equals our concentration of base. Therefore, our pH here is a neutral solution. So it's pH 7, and that's what they did here. Equivalence point, moles equals moles of acid equals moles of base. So therefore, pH equals 7. So solution is correct. Can also state that HCl is a strong acid and NaOH is a strong base. Therefore, the concentration of HCl would equal the concentration of H3O plus, and the concentration of NaOH equals the concentration of the hydroxide ion here. Good. Solution here is correct. Okay, that was a long question. So that was 7. I think we can probably do one more here. This is probably 8 here. Let's probably do question 8. It says, which salts will be more soluble in acidic solution than pure water? Explain why each salt is not more soluble in acidic than in pure water. All right. So let me write this down first. We have CuCl, CsClO4, CaSO4, BeOH2, and AlPO4. So we have copper chloride here. This is copper 1 chloride. We have this is cesium perchlorate. We have calcium sulfate. We have here beryllium hydroxide. This is aluminum phosphate. And the question is asking us, which salts will be more soluble in an acidic solution than in pure water, right? So when we're talking about solubility, actually, I'm going to actually, for the sake of time, what I'm going to do is I'm going to actually look at the answer, just verify it and kind of teach you the concept of this, actually, just because it's the last question of the day here. And I kind of want to finish on time. So it says, which will be more soluble in acidic solution than pure water? So we're comparing, here, let me do this in blue. We're comparing water and acidic solution. This is water versus acidic solution. So it says here, the solubility of a substance is defined as the amount of substance that's dissolved in a particular volume of solvent. That's good. So we have the association of copper chloride and cesium chloride are as follows. That's good. So they just broke them down into their ions, right? So we have copper and the chloride ion. That's good. We have cesium and the perchlorate ion, which is good. Calcium, we have obviously the calcium and the sulfate ion. We have beryllium and the hydroxide ion, and aluminum and the phosphate ion, right? So they kind of drew, they have all these ones here. And it says, in this reaction, chloride and the chlorate ions are passive, that are not readily soluble in hydronium ions. Thus, they are insoluble in acid solution. So what we have when we're talking about this this kind of topic here, it says chloride and chlorate anions are passive. So it says here Cl minus and ClO4 minus are not soluble in acidic solution. So let me draw that. Let me write down what that means. So we only care about basically the anions, right? So we have Cl minus and we have ClO4 minus as well. And basically what it's saying is we're going to kind of we have acidic solution. So we have you can think of it as H3O plus, right? Because it says they're not readily soluble in hydronium ions. So this here would be, you can think of it as H3O plus and H3O plus here. And they're passive and are not as readily soluble in hydronium ions. So thus they are not soluble in acidic solution. So what we have, if we were to basically write a reaction, we would get HCl and H2O, and for this one we would get perchloric acid, HClO4, and we would get we have water actually. But if we don't have H3O plus, for example, if we had actually an acid, so let's think of an acid, let's say H2SO4, for both of these guys here, would this actually give us a reaction? In this case, we'd actually have to look at our anions here. We have Cl and we have SO4, ClO4, and SO4, right? So what we have here is that would this actually displace SO4 for us to kind of break down our to make it soluble? In this case, it wouldn't, right? Because we have Cl here versus sulfate here. Sulfate is a much bigger ion, and Cl isn't, right? So this can't kind of like displace it, right? You can think of it in terms of electronegativity, sulfate and chlorine. Same with the kind of you can think of it as activity series as well versus perchlorate versus sulfate as well. So these guys wouldn't actually be insoluble. So this here would actually not give us a reaction here. There'd be no reaction here. So therefore, these are not soluble. And then finally, for these three guys here, we have calcium and sulfate, which is good. They just showed the dissociation. Beryllium and hydroxide, that's good. Aluminum and phosphate, and these guys are more soluble in our acidic solution, right? Because if I were to write it down, calcium sulfate and H2SO4, for example, sulfate would actually displace chlorine. So for example, if my acid here was HCl plus CaSO4, I would actually get calcium chloride plus I would have H2SO4. I would get sulfuric acid. So in this case, it would actually dissolve. If I were to dissolve beryllium hydroxide, HCl plus BeOH2, this one would actually be a neutralization reaction, right? You have a base and an acid, right? So this here would become BeCl2 plus H2O. So this is a neutralization, which will definitely be soluble. And finally, I have aluminum, so HCl plus AlPO4. In this case, I would make H3PO4, so phosphoric acid, and I would also make aluminum trichloride, right? Aluminum chloride here, not trichloride, sorry, aluminum chloride here, right? So this here would be our solution here. These three would be soluble, whereas copper chloride, chloride, and calcium, cesium perchlorate would not be as soluble. So this here is my answer. This here is a great solution, good solution, and step-by-step analysis. I liked how they wrote the dissociation reactions for all compounds. So these guys are good, which means solution here is correct. Solution here is correct, and that will be my final answer for that's my final question for today. Again, we're running out of time, so I'll probably save this question for next time. Next time I'm going to do another grade 11 session. Again, if you were in the chat, thank you so much for watching. You can definitely tune into OneClass, and you can tune into my teaching. I stream from Monday to Friday. Monday, Wednesday, Fridays are my math sessions, and Tuesdays and Thursdays are my chemistry sessions. Again, thank you so much for watching. I'm going to stream again in about an hour. We're going to head into some grade 12 material for grade 12 chemistry, and I'll probably do a couple questions from kind of that course as well. If not, I thank you for watching again. Stay safe, stay healthy, and have a great day. Take care.